First and foremost, thank you to the program committee members for inviting me to give this keynote. The topic is software techniques to mitigate hardware transient execution attacks. Now I'm going to talk about my experience in this area, classifying and developing mitigations, including for a recently disclosed potential vulnerability called load value injection. And I'll attempt to provide some perspective on where we are, how we got here, and where we're going as an industry. And Intel recently updated the terminology that it uses to discuss transient execution attacks and side channels. So I'll also talk about that and why it is important to have precise terms to help convey complex ideas. So who am I and what do I do at Intel? I'm a security researcher in Intel Labs. I look at hardware and software mitigations for side channel attacks and transient execution attacks. I also play a role in the Intel Product Security Incident Response Team, the IEEE. Now, if you happen at any point to find any potential vulnerability affecting Intel products, either hardware or software, this webpage provides guidance on how to submit your findings to Intel and begin a dialogue with the IEEE. Then IEEE members such as myself will investigate the findings and determine the best way to provide clear guidance on the solution, impact, severity, and mitigations if necessary. On January 3rd, 2018, proofs of concept for new potential vulnerabilities dubbed by researchers as Spectre and Meltdown were disclosed publicly. But at the time, I was not at Intel. I was actually in the thick of my dissertation writing at Syracuse University. And I didn't pay very close attention, at least not that day. In case you're wondering where you might have seen this building before, fun fact, it is rumored to have inspired Charles Addams's image of the Addams family house. Anyway, the next morning, my dissertation advisor emailed me and said, "Good timing for your dissertation topic. Memory content leakage due to timing attack-based side channels due to speculative execution at the processor level." Okay. He seemed to think that my dissertation work could be highly relevant given that both topics ostensibly covered side channels. So at this point, I thought to myself, well, okay, so I guess now I have to pay attention. So I set my dissertation work aside for the time being and read the two papers that had just been published. Now, after slogging through them, I reached a couple of conclusions. First, I didn't see any path for my dissertation work to address this new topic. And second, at this time in January of 2018, I had also just wrapped up a survey of side channel attack history that I would later include in my dissertation, covering about a dozen or so of the seminal works on side channel attacks over the past few decades. And after reading these two papers, Spectre and Meltdown, they didn't feel like side channel attacks at all to me. They didn't fit the mold, but were instead more like a new class of vulnerabilities. They represented something related and yet also somehow unrelated. So in order to examine and appreciate the breakthrough discovery of these vulnerabilities based on speculative execution, it is helpful to do a brief review of side channel research. The first use of the term side channel appeared in 1998 in a paper published by John Kelsey and other researchers. The paper was a generalization of some work published 2 years earlier by Paul Coker, who, by the way, 20 years later, would again appear as a pioneer of transient execution attacks. So Kelsey defines a side channel attack as an attack that, quote, occurs when an attacker is able to use some additional information leaked from the implementation of a cryptographic function to cryptanalyze the function. Since the publication of this paper, the term side channel attack has, of course, been broadened to cover more than just cryptographic algorithms, but otherwise the definition hasn't changed a whole lot. The key aspect is that side channels arise from the algorithm's implementation. For example, the number of clock cycles consumed by a cryptographic algorithm running on a given platform and for a particular key. That's the kind of example that was examined in this paper. So this stands in contrast to traditional cryptanalysis that has been around for centuries, where the goal is typically to derive plain text or key material from a given ciphertext, or in other words, derive a cipher's inputs from the cipher's output. Of course, there are other implementation details of a machine that can inadvertently leak information in a similar manner. 1 year later, Paul Coker and others demonstrated that by measuring the power current drawn by some computers, they could gain some insight into the behavior of a data encryption standard implementation. The top and bottom of the figure show two traces of power measurements taken for the same function, one with a branch taken and the other without. The highlighted area shows how the power signal differs depending on whether the branch is taken or not taken. And the authors actually give 5 examples of key-dependent DES operations that at the time would have been implemented with conditional branches and therefore could potentially leak key material. Somewhat loosely related to side channel attacks are the suitably named reaction attacks. They assume that the adversary has some means to visually monitor the victim. I mean, literally, the victim's physical body, facial expressions, gestures, in order to read signals from the victim's reactions while operating a computer or, say, an ATM machine. The authors showed that by flipping bits on the ciphertext that is used by the Mitigations public key crypto system, they can then observe when the victim would grimace or squint when some text or images decrypt incorrectly. Mitigations is somewhat interesting because it uses error correction. So there is some tolerance for errors in the ciphertext. So what the attacker does is iteratively flip bits in the ciphertext while observing the victim using the machine. The victim's visual cues would reveal when a flipped bit has exceeded the capacity of the error correction scheme. And then by reverse engineering the error correction vector, the attack can eventually recover the plain text. Now, this type of attack I find really interesting, in part because the side channel, if you can call it that, and I think actually it is fair to call it that, is a human being. And human beings are, of course, notoriously vulnerable to cyber attacks. And now we arrive at what is arguably the most widely studied side channel in academia, and that is the state of a set associative cache. The popular prime and probe technique was first introduced in 2006, and it proceeds in 3 steps. In step 1, the adversary loads enough cache lines that map to the same cache set to fully saturate that cache set. Then in step 2, if the victim accesses some data that maps to the same set, the adversary's data is evicted from that cache set. Then a subsequent probe in step 3 of the same set by the adversary will be measurably slower if the adversary's data was evicted by any of the victim's data. But although these researchers were the first to demonstrate these novel side channel attacks in the 1990s, early and mid 2000s, another use of these channels had actually been discovered more than 2 decades prior. So in 1973, Butler W Lampson published this really terrific paper. And while we're at it, I have to recommend that you go back and read old computer science papers from like the 60s, 70s, 80s. It is totally fascinating to get a perspective on some of these problems from like a half century ago. And the papers are usually very concise, and they convey complex ideas in just a few pages. And I often get the impression when reading them that today's academic papers have become unnecessarily verbose, my opinion. So anyways, Lampson published this note, and in cybersecurity, it's like a fossil because it predates the Morris worm by 17 years. And so Lampson is just listing out all the ways that data can escape from a system where it's supposed to be confined, right, within a service, so that the service owner can't access it. Kind of foreshadowing for the modern cloud era, right? 1973 again, pretty impressive. And he describes this concept that he calls a covert channel. Lampson says that covert channels are those channels not intended for information transfer at all. And he gives this really clever and insightful example of a computer varying its I/O ratios to encode a high or a low signal and secretly or covertly transfer information to someone such as the service owner, who should be otherwise prohibited from having access to that information. So the paper is totally brilliant, in my opinion. One reason that I bring up this parallel topic of covert channels is that there is occasionally debate or disagreement about the meaning of these two terms. And I also sometimes see academic papers, also in industry, where they're being used interchangeably or inconsistently, and it helps to be precise. Now, as I interpret these terms, in the original documents where they appear, and as most people generally seem to use them, they have these meanings. It's a covert channel if the adversary controls both input and output. It's a side channel if the victim is unintentionally leaking data to the adversary who's monitoring, observing the other end of the channel. Now, at some point, this is working at Intel, I had struck up a conversation with one of my colleagues, and I was complaining about how the industry, mostly the industry, and to some degree academia, had been jumbling these terms for years, even decades. And his response was that it doesn't really matter because side channels and covert channels are basically the same thing. Now, coming out of academia, I wasn't really sure what to make of that argument. I just thought of them instinctively as very different concepts. But he claimed that if you look at any kind of computer architecture or microarchitecture document, it's not like you can just point to one component and say, oh, that's a side channel, or, oh, that's a covert channel, but it's definitely not a side channel. And then he challenged me to build a formal model of a Turing machine with distinguishable concepts of side channels and covert channels. I thought I could, so I tried, and I pretty quickly realized that it wasn't exactly possible, or at least it wasn't possible without introducing abstract notions of principles like Alice and Bob, or adversary and victim. But this colleague insisted that Turing machines don't have abstract principles, and therefore that side channels and covert channels must be isomorphic. They must be the same thing. At this point, I was about to give up when I came up with what I thought was a more compelling argument. I said to him, okay, so there are plenty of academic papers that describe how a certain channel, such as a cache, can be used as a covert channel to transmit data and as a side channel to observe and infer data. And when the channels are used in these two different ways, the channels sometimes actually have different properties, like different bandwidths or different levels of noise. And moreover, that this distinction makes these distinct terms useful. My colleagues somewhat agreed, and after thinking it over for a while, we both identified the gap in comprehension. I had always interpreted covert channel and side channel as characterizations of a channel in a threat model, in which case they are different. Whereas he had always interpreted them as attributes of a physical machine, in which case they are the same. So it occurred to us that maybe the classical terminology in the space was simply lacking. So what we came up with, and this didn't happen overnight by any means. It took a few weeks, I recall, and a lot of contentious debate at times. We came up with this, that channels, I mean, the concrete kind that you can point to on a computer architecture specification, are of two sorts. So we again borrow a term from Lampson, legitimate channels, and anything that is not a legitimate channel is an incidental channel. So basically, any channel that was not explicitly designed to transmit information is an incidental channel. It may transmit, it may signal information, but this is incidental to its intended purpose. Incidental channels can then function in one of two ways, depending on the context of a particular attack or threat model. An incidental channel functions as a covert channel if the adversary controls both ends, and a side channel if the adversary only controls the output end. So that does align with the original intent of those terms. Now, after that brief and pedantic digression, let's return to January 3rd, 2018, and Spectre. The paper includes a code snippet like this, often referred to as bounds check bypass. And the microarchitectural instruction stream is depicted at the bottom of the slide. There are 4 steps in the proof of concept. First, the adversary will train a microarchitectural branch predictor to anticipate an inbounds array index. And then the adversary will provide an out-of-bounds index, thus triggering a speculative misprediction. Any instructions executed following a speculative misprediction are executed transiently, meaning that the instructions are executed by the processor, but they never retire and commit to the architectural state that is visible to software. Instead, those transient instructions are said to be squashed, and from the software's perspective, it is as though they were never executed. However, and this is the key insight behind these papers, the transient instructions may leave some microarchitectural residue, for example, in the CPU's cache state. And that's precisely what will happen in steps 2 and 3. So in step 2, the load from array 1 may transiently read out of bounds data. And then the subsequent memory access in step 3, again transiently, may then use the data that was accessed out of bounds to access memory, thus encoding some bits of that data into the CPU cache state. Now, eventually, the CPU will revert, it will squash to the point where the misprediction had occurred, and then the CPU will proceed down the correct execution path, the architectural path. At that point, or beyond that point, a cache analysis technique like prime plus probe, which I showed on an earlier slide, or flush plus reload, can be applied to extract the data that had been transiently encoded in the cache state. Now, can this behavior be prevented? Yes. In some circumstances, speculation can be muted by inserting L-fence instructions following each end of the branch. So L-fence is designed as a speculation fence, meaning that instructions will not be able to execute transiently after the L-fence until every instruction, including the branch on which the prediction is formed, until every instruction before the L-fence has retired. So in this example, steps 2 and 3 would be unable to execute. And now for the important question. Is Spectre a side channel or a covert channel? Well, it's a bit easier to understand with this diagram, depicting the flow of some secret data traveling through the gadget from the victim to the adversary. The red rounded boxes in the diagram indicate adversary code executed within the adversary's software sandbox. And the combination of access and transmit instructions, those two array access operations, so the combination of those two instructions is often referred to as a disclosure gadget. And after the secret has been encoded into an incidental channel, a kind of data transmission, then a cache analysis technique like prime plus probe can be used as a receiver to recover the secret that had been transmitted by the disclosure gadget via the cache channel. Since the adversary controls both ends of the incidental channel, that is, the adversary controls the transmitter and the receiver, the dashed arrow shows an incidental channel that is serving as a covert channel. We've given this particular category of transient execution attack a new name, an in-domain transient execution attack, because the adversary and victim are co-located in the same hardware domain, such as a process, and are possibly sandboxed using managed runtimes or software fault isolation techniques. So the whole thing isn't exactly like a side channel or a covert channel. It's actually a complicated attack composed of multiple pieces, one of which is a covert channel. And this is why these proofs of concept represented a significant breakthrough and a stark departure from previous side channel research. Now, let's change gears. For those who aren't already familiar with Intel SGX software guard extensions in the audience, it is a trusted execution environment that can be created by user mode applications and provides confidentiality and integrity for code and data within what is called an SGX enclave. There are plenty of other places to find tutorials and deep dives into SGX. For the purpose of this presentation, however, it suffices to know that the page table entries for an enclave are maintained by the operating system or the virtual machine monitor outside of the enclave. I should note SGX has a particularly strong threat model that actually excludes the operating system or the VMM from the trusted computing base. And therefore, the operating system may manipulate the enclave's page table entries, including, say, present bits, access bits, dirty bits, etc. Now, in April of 2019, a group of academic researchers submitted a ticket to the IEEE describing a technique that they called load value injection. They had built a proof of concept targeting Intel SGX, and it looked something like this. The first instruction stores some untrusted data into address ABCDE000. Totally benign. It's not assumed that the enclave program may use this data in an architecturally unsafe manner. However, many modern out-of-order CPUs will actually place stored data into a store buffer on their way to memory. And this enables several optimizations. Okay, so then sometime later, a load is issued and, oh, it faults. Maybe the present bit on a PTE had been unset by the operating system. Now, under certain conditions and for certain microprocessors, the CPU may continue to execute several transient instructions, including the faulting load and possibly other instructions that depend on the loaded value. Moreover, a value sitting in a store buffer and whose address 4K aliases, so aliases in the lowermost 12 bits, the load address may be forwarded to instructions that consume the loaded value, and such as the jump instruction in this example. So if this happens, it can potentially steer execution to an adversary chosen destination within the enclave. So when the IP search started to look at this, we started by trying to figure out how to find gadgets like this using static or dynamic analysis methods. And after looking at it for a while, we concluded that it was pretty difficult. Static analysis is most useful when analyzing architectural data relationships, such as the one between the load and the jump instructions, which share the RAX register. But there isn't any obvious relationship between the store and load instructions, which write and read from two different addresses that merely alias in their bottom 12 bits. Static analysis of this sort for aliases is possible, but highly, highly imprecise. So if you want to catch all of the possible aliases between stores and loads, you need to be really conservative with the analysis. And although I just showed an example that used the store buffer, as we explain in the load value injection deep dive that you can find on Intel's website, these forwarded values can come from other microarchitectural structures like load ports and line fill buffers. And so you may have to analyze many combinations of loading and storing instructions within each enclave function, even though very few of these combinations could realistically forward data in a manner that could be useful to mount an attack. And dynamic analysis is also really tricky because things like, say, heap allocation are not necessarily deterministic, so it also isn't really conducive to the kind of alias analysis that we would require. Now, at this point, it seemed like maybe we were stuck. And the researchers had come to the same conclusion, that the analysis to find potential LVI gadgets and mitigate them would be very difficult. And they thought that full mitigation would require inserting an LFENCE instruction after every load. So could we possibly do any better? Well, we took a step back. And in the meantime, one of my colleagues had put together a very thorough taxonomy of all of the possible shapes for LVI gadgets. We concluded that all of them share the same basic template, a kind of canonical form that looks like this. So first, something happens, either a load or a store that puts a value into a microarchitectural structure. And then the second instruction, a load whose load address 4K aliases with the prior load or store, that instruction faults, and the previous value is forwarded to the third instruction, some kind of a branch or a microarchitectural transmitter, such as a memory access. Now, if you're at least somewhat familiar with speculative execution, you might think that there could be two solutions to mitigate this kind of gadget. Either you could place an LFENCE between the prime and the load instructions, the first and second instructions shown at the top, or between the load and transmit instructions shown at the bottom. But the first solution is actually not valid, because in load value injection, transient execution only begins after the load. I mean, the second instruction, the one that could fault. So if the LFENCE is instead inserted between the load and the transmit, then any fault that is triggered during the load will be caught at instruction retirement, which the LFENCE guarantees will happen before the transmit instruction can be executed, even transiently. So even if it were possible to accurately, to precisely analyze and find all of the 4K aliasing relationships between loads and stores and each function in the enclave, this doesn't actually help at all when applying mitigations. It turned out to just be a kind of red herring. The architectural data dependency, however, between the load and the transmitter is tractable for modern compilers and static analysis techniques to determine precisely. So to fully mitigate load value injection, we don't actually need to consider the prime instructions at all. And since indirect branches can also serve as transmitters, then for brevity, we can lump the transmits and branches into a single category, just call them all transmitters. And hence the true canonical form of an LVI gadget is a pair of a load instruction and a transmitter instruction whose operand depends on the loaded value. So to clean all that up, we just need to find patterns that look like this, and then interpose an else instruction between the load and the transmitter. And in fact, what having this canonical form means is that we don't, as the researchers had asserted, actually have to place an else after every single load. Instead, it suffices to ensure that every load plus transmit pair of instructions have an interposed else. So we could just as well, we could have a sequence of instructions like this, where say T1 is some instruction that would transmit the value loaded by L1. T2 would be a transmitter that transmits the value loaded by L2, etc. So a naive approach would be to place an else after every load, or alternatively before every transmitter. But plainly, in this particular example, it suffices to put just a single else after the third load. So we can visualize this as a kind of graph problem with edges or arrows drawn from each load to each corresponding transmitter. And ideally, we would like to insert the minimum number of else that suffices to cut all of the edges. And it turns out that it's pretty easy to write an efficient algorithm to optimally insert else into straight line code. But of course, real functions often have complex control flow with conditional branches and loops, and computing a minimal else insertion quickly becomes very non-trivial. Interestingly, a very similar problem had already been examined in a very different context. This paper was published in 2015, so 3 years before Spectre and Meltdown, and also before else was being used as a speculation barrier. The authors were looking at ways to automatically transform legacy source code so that it could be used in parallel high-performance computing applications. And to do this, they needed to enforce certain memory ordering constraints with load fence, store fence, and mfence, the classical memory ordering instructions. So they described an algorithm that, given a data flow graph showing the relationships between load and store operations, would insert a minimal number of memory ordering fences to enforce the required memory orders. And the result, it was pretty impressive because they were able to demonstrate that their algorithm produced better, more efficient code than some existing hand-optimized examples. And it turns out that this technique was just similar enough to the problem that we were trying to solve with load value injection. So here's the adapted LVI mitigation algorithm at a high level. We use the static single assignment form available to most modern compilers to extract data flow relationships between loads and their respective transmitters. And we project those relationships onto the function's control flow graph. Then the goal is to use this information to compute the smallest set of else insertions that mitigate all of the potential LVI gadgets. This set of else insertions is given by the bit vector x, called the cut vector, where each bit corresponds to a control flow edge, and the bit is 1 if the edge is to be cut by an else and 0 otherwise. We also have a cost vector c that associates each edge in the graph with an integer weight proportional to its loop depth, because the cost of inserting an else instruction into a loop is compounded by the number of loop iterations, which in turn is compounded further by nested loops, etc. And finally, we construct a cost function for else insertion as the dot product of the cost vector and the cut vector. Now, as I said before, each bit of x corresponds to an edge in the graph. control flow edge in the graph. So the 1 bits indicate the edges where an L fence should be inserted. And we subject this minimization to the constraint that every path that can be followed from a load to a transmitter must receive at least 1 cut. Now, this is a well-known problem in algorithms. It is called the minimum multi-cut problem. And it can be solved by a mixed integer programming solver. So you can see in the graph here on the right that the output of the algorithm would compute 2 cuts for a cost of 2. And the significance of the output is that the algorithm avoided making a cut into the loop. So it found the cheapest, the computationally cheapest possible solution to mitigate all of the gadgets. Now, one unfortunate drawback of this approach is that there is a lot of complexity. It is a very demanding algorithm. The paper's authors observed that to apply it to a single function, not even a very large function, just a couple hundred lines of code, could take anywhere from roughly 5 to 45 seconds. So it would seem on the surface that this approach might be infeasible if you wanted to implement it in a compiler. However, upon further reading into the paper, they did an implementation of this algorithm called Perry, and it's not totally optimized. So they do the data flow analysis in LLVM, and then they export it into like an XML file that is then imported into a Python module. And all of the graph algorithms are implemented in pure Python, which then produces another text file containing the parameters for the minimum multi-cut, which is then imported into the SAGE mathematical framework, like an open source alternative to Mathematica or MATLAB, which uses GLPK, the GNU Linear Programming Kit, to solve the minimum multi-cut problem. Then the output from the multi-cut is used by yet another program to transform the source code by inserting the memory fences in line. So we wondered whether this algorithm could become more tractable if it were implemented entirely in C++. Now, there was only one way to find out the answer to this question, right? We had to go and actually implement it and see how long it took. So similar to Perry, we also use LLVM to build a data flow graph, but this time showing potential LVI gadgets instead of memory orders. The red dashed edges on this graph are gadget edges, meaning that the source is a load and the sink is a transmitter, corresponding to the load. And the solid black edges are control flow edges, annotated with the loop depth. The second step is optional. If the current function has any existing L fences, the control flow edges to and from each fence are removed, indicating that transient execution cannot cross this part of the control flow graph. And then the gadget edges that are fully mitigated, meaning that they become unreachable from source to sink, the gadget edges that are mitigated in that way are removed. So then the graph is rebuilt. And the remaining graph is transformed then into a matrix representation of the minimum multi-cut problem that can be understood by a mixed integer programming solver. So for this, we use the open source Symphony solver, which has the Eclipse public license. The solver returns the bit vector containing the minimum multi-cut. And then we again use LLVM to optimally insert fences into the intermediate representation. These are eventually emitted in the final binary. And in fact, doing this entirely in C++ turned out to be pretty efficient. We were able to, for example, build OpenSSL with only about 4% overhead overall for all the compiling and linking steps. And we found that the approach may insert up to 93% fewer L fences than what the LVI researchers had suggested in their paper. That is simply inserting an L fence after every single load. So this mitigation is now broadly available as part of LLVM Clang and also the Rust SGX SDK. We are grateful to engineers at Google for helping with the LLVM reviews and also to engineers at Fortanix who upstream the mitigations into the Rust SGX SDK. And now newer processors are not affected by LVI. You can find, for reference, a complete list of affected processors on Intel's website. So now the essential question. Is it a side channel or a covert channel? And recall that covert channels are controlled at both ends by the adversary, on the output end only for side channels. So what is LVI? Well, the adversary must manipulate transient execution in the victim's enclave to jump to a disclosure gadget within the same enclave. The orange semi-rounded boxes indicate the transient execution that is being manipulated. And meanwhile, the adversary's own receiver code resides outside of the enclave. Therefore, the victim and adversary occupy separate hardware protection domains. So we call this a cross-domain transient execution attack. And because the adversary is, again, exerting control over the disclosure gadget to transmit the secret, we can conclude that the incidental channel is functioning as a covert channel. The adversary is in control of both ends of the channel. And now a highly relevant question. How is this helpful? The exercise in terminology probably seems pedantic, but it really does actually help to clarify the impact of these potential vulnerabilities in at least two key ways. So first, it clarifies the relationships between different transient execution attacks, and we think that's very important. For example, there is actually a close relationship between load value injection and another potential vulnerability that was disclosed earlier in 2019 called microarchitectural data sampling. There isn't much time to go into depth on microarchitectural data sampling today, but on the surface, if you read the papers, it seems very different from load value injection. However, the underlying transient execution primitive is identical, namely forwarding stale data from a microarchitectural buffer on a fault. The only difference between the two transient execution attacks is the location of the disclosure gadget. So in load value injection, the disclosure gadget is located in the victim's hardware domain, whereas in MDS, the disclosure gadget is in the adversary's domain. And this qualifies it as what we call an example of a domain bypass transient execution attack, where the adversary executes transient instructions in its own hardware domain that circumvent hardware-based access controls. So the second way that this terminology helps is to concisely convey the impacts and mitigations of transient execution attacks, according to each of the three categories we have described in the terminology white paper. By the way, highly recommend it, linked at the bottom of this slide. For example, cross-domain transient execution attacks, such as load value injection, may require compiler-based mitigations to find and suppress potential gadgets in a given code base. Domain bypass transient execution attacks may be addressed by new hardware, by microcode updates, or occasionally by updates to the operating system or VMM. And Intel has a separate white paper with comprehensive guidance for potential vulnerabilities described as having an in-domain impact, affecting those managed runtime, software fault isolation, software sandboxing scenarios. So that's a glimpse of where we stand today. Now, where are we headed? What comes next? Fortunately, new processors are designed to mitigate many of these potential vulnerabilities. For example, LVI and many others. Intel has been actively collaborating with many universities through a side channel academic program that was launched in 2018. And in just over 2 years, we've seen 92 papers come out of this program, including 67 Tier 1 conference papers, and among those, 15 Best Paper Awards. This breadth of research has covered not only defensive research like mitigations, but also offensive research, including, for example, load value injection. Transient execution attacks and their mitigations it's still a nascent area of research. It hasn't even been 3 years. And there are many avenues to explore and develop new mitigation techniques in both hardware and in software, as well as to improve upon some of the existing best known methods. And on that positive note, I will conclude. Thank you very much to all of you for listening. And once again, to the program committee, be happy to entertain some questions.